Hi, everyone. Welcome back to Bufnagle the podcast, where we explore entertaining and enlightening discussions of the adventure of life and all things good. From science and technology to history and philosophy to leadership and success. We hope to give you a better understanding of the world and skills for everyone to pursue their own adventure.
Started the episode without me knowing.
I didn't get much on it.
Not really. I saw it coming. Hey, ladies and gentlemen, welcome back to Bufnagle, the podcast, where we talk about all things good in the pursuit of the adventure of life. I'm Harry, and I'm joined by Rafe here this morning. We're recording in the morning, which poses a lot of interesting dilemmas as far as children go.
Yeah, it's I have to say, I don't have that worry anymore, which is a good thing. And the lawnmowers in the neighborhood seemed to come by yesterday. So I should be good, but we may have to mute your mic from time to time.
Yes, I may have to mute, and you just might have to monologue for a little bit.
We'll see what happens. So anyway, before we get going, I just want to make sure everybody recognizes we have the world's greatest listeners, and they are the reason we have achieved a rank of the Global Top 10% podcast. As usual, you and they can reach us at bufnagle@bufnagle.com. Remember to share the love, share the buff, give us a 5-star review, subscribe, like, hit the smiley stars, whatever else is on there that makes my life better, Harry's life better. Those things will make your life better. Remember, tell a friend to listen, and you will get a free episode. Harry, last time we were talking about light, we were talking about Michelson and his ability to demonstrate the speed of light. And he demonstrated it goes really, really, really fast by being very clever with spinning mirrors and
very accurately too.
Yeah, and geometry. You know, that's a reason to take a geometry class, so you learn how to do all those angle kinds of things.
Yeah, and I don't know if your geometry class was similar to mine, but I feel like my geometry class was less geometry and more proofs, which as a 12-year-old is probably not the right time to do proofs.
Is that
when you would focus? They always pair together geometry and proofs. I did it in 7th grade.
See, I took it as a sophomore in high school, geometry.
Well, they've watered down all mathematical courses.
So they can
that way you can do calculus in high school.
See, but I don't think you can do calculus. I mean, you can manipulate the symbols and you can get an answer. But okay, this
we're already off the rails here.
This guy, you can't do it. All right, and the reason you can't is if you spend a lot of time working with like falling body, like if you play a lot of baseball. Okay. Mm-hmm. And you see the ball flying around, it goes up and it comes back down. And if you shoot, projectiles, arrows, and if you have cannons in your backyard, that sort of thing, if you're doing those kinds of things, if you're physically pushing sleds across,
if you're dealing with flow rates of water in pipes,
well, yeah, and if you're doing things like riding your bike and shit, like, but at some point you have to have enough life experience to make those things go. To understand what it is that you are doing with regard to understanding that rate of change of position is velocity and rate of change of velocity is acceleration. I mean, that's where you get, Newton invented the calculus to help him understand and describe the motion of the planets. And he was not a 12-year-old. I mean, what 12-year-old can do that? They can manipulate. It's like a really good child musical prodigy. They can make the keys on the piano make the notes in the right sequence at the right time.
Sure.
But they don't have the life experience. They don't have the understanding of the nature of being human. They don't have that until they get older. And I think that's part of the thing. I think we want to say, hey, we're doing calculus for 8th graders. It's like, they don't get it. They don't get it. They know how to manipulate the symbols, but they don't recognize. They can't, and it's not their fault. They just can't recognize it at 12. So We did it as sophomores in high school, and we did a lot of proofs. We did a little bit of trig. Actually, we didn't do trig in geometry. We did trig in what was called
trig.
Well, we did what was called college prep math, which was a 12th grade thing, and we did like a semester, almost a semester of trig, and we did the formal definition of a limit. In high school, we did that. In college prep math, we spent weeks on formal definition of a limit. And then we did some other kinds of things. We did a little bit of probability, and we did some...
Well, yeah, I mean, that kind of falls into everything has been watered down now to a point of, can you just manipulate the problem to fill out the regular problem sets?
So as to take the AP exam?
Sure. Yep.
Yeah. Okay. All right. I'm sorry. Side note, maybe... Okay. That's a preview of coming attractions. But anyway, Michelson was not a 12-year-old when he was figuring out the speed of light. He was a very bright graduate of the U.S. Naval Academy, and he was there now working there. And he determined that light moves at 186,000 miles per second, or 3 times 10 to the 8th meters per second, however you want to measure those things. But still, the question of what is light remained unanswered. There was man had struggled with this, as you can imagine, for ages. Newton thought that light might be little tiny particles that get released from a hot object, and then they go shooting out, and then they bounce off of whatever they bounce off of, and they hit us in the eyeball, and they trigger our eyeballs to have us recognize light. There were other people that thought that light, that vision was like your body going out and reaching to something, like your eyes actually shot something out that bounced off the thing and then came back. But they demonstrated somehow that wasn't the case. And some people thought it must be a wave. But there were some things about it that didn't behave very wave-like, at least from what they could see. So they thought, well, maybe it's like sound. All right. So what we're going to do is we're going to start with sound here and talk about how sound works. And then we're going to tie it, see if light kind of does the same kind of things.
Sure. So right? It should bounce off of things. It should vibrate in some way.
Yep.
It should.
Well, the other thing it should do
is it should move through the air.
And it should move through the air. And it should move through other things too. Sound moves very well through water.
Yep. Through a medium.
And through it can move through solid objects like wood. Right, those things you can transmit sound that way. So the Greeks knew about sound. Okay, you can read ancient Greek stuff, and they understood the concept of sound, and they recognized that sound was generated by something like a string or a tuning fork or something. You can even feel your throat vibrate when you talk. That sound is something vibrating, and what it does is it pushes and pulls the air that's around the vibrating thing, and it makes what we now call a compression wave. So the air that's fluttering around the vibrating thing gets pushed, and it pushes other air, which pushes other air, which pushes other air. But that creates kind of a decompression thing behind it, and then that air kind of flows back in. So the air goes out and in, out and in, and essentially there's no net movement in the compression wave. The air doesn't move when the wave goes through it. And just like if you throw a rock into the water and you send a wave out across the water doesn't move. It just goes up and down, but it doesn't move in the direction of the wave. The wave doesn't produce any net motion. So compression waves are what makes sound, and they get pushed back and forth. And then that compression wave goes into our ears, which causes our eardrums to wiggle, which moves some little tiny bones, which triggers some nerves, which makes sound, which is
incredible.
It's absolutely unbelievable. Certainly when you understand what's going on past the eardrum, like on the ins. Now, I don't think the ancient Greeks really understood those little tiny little bones and how the nerves were working. But that is just a remarkable thing that there's this little miniature. Well, it's the same way as the
smallest bone in your body, right?
Yeah, there's 3 of them in there. There's like what do they call it? There's a hammer and a sickle, or
and a nail, and I don't know.
Well, there's one of them's a hammer, right? Hammer and a stirrup, and you can see when you put them together, you can see how the mechanics work, and that's just remarkable stuff. But the nerves in your brain, in your ear, send signals to your brain that encode the intensity or the loudness of the sound. and the pitch, the frequency, whether it's a high pitch or a low pitch, or that your ear picks that up. All right. So, but the other really cool thing about waves is they possess this quality called interference. Right. And so they add up, I guess, and they add up positively and negatively. So you can get two waves that cross each other, and you can get zero depending on where the troughs and the waves come through.
And that's exactly what noise canceling headphones are.
Yeah, that's exactly what they do. They read the noise that's coming into your head. They create a wave that's exactly the same but upside down, and they project it at the same time, and your ear doesn't hear anything because there's nothing there for it to hear. So the amplitudes of the waves that are the sound waves of the compressor waves, those amplitudes add together. Okay, so an example of that, you can take a rope. All right, you take a piece of, what do they call it? What is that cord that you guys use in the Army all the time? It's like 550
paracord.
Yeah, 550 paracord. Take a piece of 550 paracord, 10, 12, 15 feet long. You at your, reach into your drawer of things that you have in the kitchen there.
I've still got a big bucket of Army stuff sitting in the garage. Yeah. I'm sure there's someone there.
Yeah. So, and tie one end to like the doorknob, and then stretch it out, not so tight that you can't wiggle it, but stretch it out, and then send a wave, down that rope. Okay. So snap up and down, and that wave will travel down the rope, and then it will bounce off the door, and it'll come back to you upside down. It comes back. It goes there and back. Yeah. And that's not a compression wave. That's it's a rope wave. But you can see what happens when you lift the rope real fast and push it back down. The little bit that's in your hand lifts the part that's next to it, which lifts the part next to it, right? And the lifting thing is what travels down the rope. It's energy. Wave is energy. And the energy is making the rope move. But there's essentially no net motion in the rope. The rope goes up and down, but it doesn't move back and forth to and from the door. Now, if you do that and you stand there and you send a bunch of those waves down the door and back, you will see that if you do it at the right frequency, you can get them to come down and back, and you can create a standing wave in the rope, right? You've done that. You wiggle it.
Looks like it's not moving.
Well, yeah, some of the parts aren't moving, right? Some of the parts are sitting perfectly still because the waves that are going through them there's a wave going out and a wave coming back, and they cancel each other out. And that's a great thing about waves. Waves have interference patterns, and that's a fundamental thing about waves. If you can get them to bounce off things and bounce back, you can look at those patterns and you can understand things like what frequency the waves are at. And that's a fundamental trick that Michelson's going to use here coming up. So now if you send like a water wave, I guess, is that called a water wave? Can I call it a water wave?
We can call it a water wave.
Okay. You send a water wave across the surface of some water, and you send it through a slit, like a break in a breakwater. Mm-hmm. Okay. And what'll happen is if the slit is wait, make sure I get this right. If the wavelength is shorter than the slit. No, the slit is shorter than the wavelength. If the slit is shorter than the wavelength, when the wave comes through the slit, you will get essentially what we'll call a point source for that wave.
I was going to say repropagate.
Oh, well, there you go. Is that the right word?
I don't know, but it sounded
that's a really good word. We're going to use that. So if you have that situation when the wave goes through the slit, it'll be as if that little point where the slit terminates on the other side is like a point source for the repropagation of that wave. And you'll get the wave spreading out like in a semicircle across on the other side of that. Okay. So these when you have little slits like that, you can get point sources of waves, but the trick is that the slit has to be narrow enough to do that. You can't have a really wide slit because then the wave just runs right through it. It has to be the slit has to be smaller than the wavelength.
Yes.
So, okay. Those are things about waves. Okay. So is light a stream of particles like Newton thought, or is it a wave? Well, waves we know will actually bend around corners, right? And light, but light doesn't really do that. Light kind of goes in straight lines, and you get shadows, right? I mean, you can't look around the corner of a building, but you can hear around the corner of a building.
Yes. Yep.
Right. And so this interference things for light, if they are there, these bendings of things, of these waves, we people couldn't see them. All right. And with sound, we know what sound is: this compression and decompression of the air that carries the sound. And Fowler, the guy who puts these notes together for us, says that that was his.
We do a lot of our own research here by researching other people's research.
Well, that's what am I supposed to make this up on my own?
Well, I just expect you to redo Michelson's experiments by yourself.
That's what he had to redo. He did Foucault's experiments at the Academy. Well, when Bufnagle the Academy comes online, we will set up Michelson's experiments in the backyard here for summer camp. Summer light camp is what we'll have, and it'll take place at night, so you can see the lasers. Fowler says, if light is a wave, what is doing the waving? It clearly isn't just air, because light reaches us from the sun and indeed from the stars, and we know that air doesn't stretch that far, or the planets would have slowed down by air resistance. Right? So the planets are out there moving around the sun, and they've been doing that for whatever
millennia.
What's even like
Tons?
millennia? Long periods of time, billions and billions of years. Those planets have been zipping around there, and they're not getting slowed down by air resistance. So, what carries the wave? What is doing the waving? Right? It's a hard question, and in the 1800s, by around 1800, it got figured out that even though light, we don't really seem to know what light is traveling in, what's doing the waving. It does seem to be kind of a wave. That there are wave properties. By 1800, they have that. But the big issue with light is that the wavelengths are really, really, really short, like 1/50,000th of an inch. All right,
it's a little small.
Those are holy cow. I'm trying to think. It's hard for me because I can figure out an inch here, like on my the length of the tip of my thumb here, or something like that. That's about an inch, 2.5 centimeters.
Mm-hmm.
And I'm looking at that, and I'm like, I have to divide that into 50,000 little parts, and that's how big the wavelength is.
Yeah, I don't think you can get your fingers close enough together for you to see a difference.
Yeah, I got to get it really, really, really tight there. And certainly with my current prescription on my glasses, at that point, it starts becoming it gets to the point where I can't. It's within the fuzz on the peach, as they say. Mm-hmm. I can't see tighter than that. But these very short wavelengths or high frequencies, those things make light travel in straight lines. Now, if you've ever hooked up your tweeters and your woofers on your stereo, the tweeters are the speakers that make the high frequency sound, and the woofers are the speakers that make up the low frequency sound. And tweeters,
you're old. These days we just have subwoofers, and that's it.
Well, but the big issue with the woofer and the tweeter, okay, the tweeter makes the high frequency notes, the high notes, okay, and those are very directed sound waves. They have very short wavelengths, and they go straighter. They go straighter. The woofer makes these big gigantic waves that they kind of
fill the room.
They fill the room. And what you can do is, if you have two tweeters and you can get your stereo to make a constant, frequency sound, just that kind of sound, and you make it real high, beep, like a tweeter thing. There are places you can go around the room if you have two tweeters, and you can find the interference patterns. You can find, like, wow, it's really loud over here and it's really quiet over here, because those waves are coming out of the speakers, and there are places where you can feel the interference pattern in the room. Okay. And in fact, these very fancy speakers that I have in my house, there's an app on my phone that reads the interference pattern as you walk around the room, and it adjusts the speakers accordingly. Now, I don't know exactly what it does, but there are tweeters and woofers in the speakers, the box, and it turns them up or turns them down and adjusts their directionality. So
depending on where the phone is in the room, right? You got to have the phone with you.
Oh, right. What you do is you take the phone and you say, okay, I'm going to do the thing now. And the speakers start going, boom, boom, boom. They make this gigantic noise. That's why I never do it with your mom around. But
Can't imagine she likes that.
When you place the speakers in different places in the room, they tell you to I don't know if they call it calibrate or adjustate or something. They tell you to redo the balancing of the speakers to give you the right interference pattern, so you don't have. And they say start where the primary hearing location is. So like if you have a home stereo a home theater, or you have a thing like that, they want you to say, okay, so where's the main place to be? And then they set it up so that
there's less interference in the more common areas.
Right. And what you do is you take your phone during this 1 minute test, and you walk around the room, moving your phone low to high, low to high, low to high, all around the room, kind of like you're sweeping the air. And it does a thing like your phone knows where it is, and the speakers pick up what the sound is, and it does math.
We could figure this out. Right? You can, right? So
yes, you can.
You have your two tweeters in a certain location. We'll say it goes from point A to B, and halfway between point A and B is one half. You put your phone there.
Yep.
And it knows the time for the sound wave to get there to a certain point. Your phone picks up that reading and sends a digital signal back.
Yep.
Which is technically faster, right?
Yeah.
And then it will determine along all of those points how far away the phone is from each of those points and what the two tweeters are giving the phone at each of those locations.
Right. And then it will adjust. But then there's also, it bounces off the wall too, right? So it's kind of trying to figure out the interference pattern in 3 space by yahoos like me walking around with the phone. I should play the sounds of what it sounds like. But your mom went to go visit your sister. So she right now, we could do it here on the show. We'll have to.
Oh boy.
No, we're not going to do it. It takes about a minute and a half, and it's very loud and it's very fun, but it can be done. Okay. So there's interference patterns with sound, and light does that too, but not quite as, but light is very directed because the wavelengths are so short. Okay. And that's why it doesn't go around the corners otherwise. That's I think what we were doing. So, you can see some of these interference patterns in certain physical phenomena that are familiar to everybody. Okay. And those two things are soap bubbles and oil slicks. So if you look at a soap bubble and certain places on the soap bubble, you'll see you'll see colors on the soap bubble.
Right.
And what the reason you get those is that the white light that's around you in the room, hits both the outside of the water of the bubble film and the inside of the bubble film. And both of those create a reflection back to you. And they are of the thickness of the film is of the magnitude that allows certain wavelengths of light to positively interfere with their own wavelength. All right. So if you have a wave that has length 2 nanometers. I don't know. I think that's right. If it's length 2, okay, and the bubble has thickness 1, then to go from the top to the bottom and back to the top again. If you have 2 waves that are in phase that way, they will
be out of phase by 1.
Well, no, because down and back.
Oh, yep.
It's just going to be 2. So they will be in phase and they will be amplified, and that's why you see that in that area where you see that color, that's how thick the bubble is. All right. And there's some great pictures on the interwebs, if you would like, of bubbles of certain colors. And
depending
different areas.
On the thickness of the film of the bubble.
Right. And the film changes thickness throughout the bubble because gravity and those kinds of things, and soap and also saponification. There's an episode for you. So but all of those things are taking place in the bubble. And the same thing happens with oil, like in the on your driveway, or like in the storm sewer when there's a little bit of rain, and that you get those shiny, colorful patterns with the oil. The same thing is happening. You're getting a positive interference pattern from the reflection
of amplification.
Yeah. So you get that. So you get that thing that happens, and so light appears to be a wave. By this time, they're like, we're getting a lot of these wave things, and what's it traveling through? And we know sound travels through water, through air, but also through water and solid materials, like we mentioned. Light, not so much. Light seems to go through air, goes through water, not very well. It goes through empty space.
Yep.
Yeah, and that's kind of nice. But light doesn't tend to go through other things. But we found out studying sound that sound goes very fast in materials that are less squishy. So the less difficulty the sound has in making the compression wave, the faster it'll go. Yes. Well, actually, if it's really dense, like if it's dense like wood or steel, those sound goes really fast through those things. Air is less dense. So but lighter materials move it faster. So if you want the wave to go really fast, you want something that's very, very hard, very, very non-squishy, but also very lightweight. Okay. So, right. So, and if you wanted to do the same thing with light, then you would want to have some sort of stuff that it would be very light, so that the light could go. It wouldn't be very. It would be not very dense, but it would be very incompressible, which are two things that are.
So we're I think getting to the point where we are going to call this.
We're going to call this. Okay. So they knew this, and they made up this word for this. They figured all of empty space is filled with this miraculous stuff called the ether. Okay, and there's two spellings of this. Sometimes it's AETHER with that AE combination letter thing, that ligature thing that comes out of the Greek stuff. But we just spell it ether, ETHER. And they knew that this stuff had to be very light and very hard to allow light to travel so fast. But solid bodies like planets and moons and things like that have to be able to pass through it without resistance. So you're kind of up against. So this better be magical stuff. is what it looks like. Neat. All right. And they call this the ghostly wind of the ether. And they said we should find out if this really is the case. And the man for the job was our old buddy, Albert Michelson. He decides to take on this project to demonstrate where the ether is. And he concluded that we measure speed of sound relative to the air. In fact, if there is a wind, the sound gets faster downwind than upwind. Mm-hmm. Okay, so that's a thing because it's carried on the air as it's moving, and the compression wave gets carried through the air as well. So there's this kind of additivity there with the medium and the wave. So Michelson figured what I really need to do is I need to measure when I'm going with the ether, when I'm going through the ether, like into the ether or with
away from the ether.
Yeah. Then I ought to get two different speeds. Yeah, I ought to get different speeds for light. And so if I shine, like if the Earth is moving through the ether around the sun, then I'm going into the ether in one direction and I'm going not against the ether in the other direction. And I should be able to measure that. And he did that math and he figured out, wait, there's no way I'm going to be able to detect this with my machines because my machine for measuring speed of light is not accurate enough to pick up that change that's relative to the speed of the Earth through the ether. But he figured out that he could do it by using interference patterns. All right. So his plan was to take a single beam of light of a single color and split it into two perpendicular directions. One direction, he's going to go out and then back off a mirror across the flow of the ether. And one of them is going to go back and forth with the ether. So one of them is across the ether and one's with the ether. Right? And he's going to measure time out and time back. And it turns out that if you go across the ether, across and back across, like a river, if you're going across a river, right, orthogonal to the flow, that will take you longer than if you go up river and then back down river.
Yes. Yep.
Okay. And you can prove that doing Pythagoras stuff. Okay. So going across the flow takes longer than up and down. Against and with takes shorter than across and across. That's what he figured out. So he said, what I'll do is I'll shine this light that's all the same wavelength. I'll shine it out and back off the mirrors. And then when they come back, they will interfere with each other.
And should cancel out.
Well, they should cancel out because if they go the same distance. But then he was like, oh, wait, if I'm off just a little millimeter or less, like a the wavelength, just a little nanometer or like a picometer or something, a really small meter, if he's off a little bit in the measurements of his placements of his mirror, then he'll get the distances won't be the same, out and back and out and back. But he figured, well, that's all right. What I'll do is I'll put this thing on a turntable and I'll be able to spin it. So whatever difference I do have with the distances of across and width, I can rotate that thing. And all I have to do is determine whether or not the interference pattern changes when I go across or width. So as I spin that thing around, I will get an interference pattern because of whatever I will get. And if that interference pattern changes when I turn that thing 90 degrees, then there's a difference between across and width. Right. So that's what he did. So he set this thing up and he puts, he checks to see, is there any ether wind? And he runs the experiment and he finds nothing. You spin the interferometer, you spin it around and you don't get any differences, right? And everywhere he looked, the interference pattern was the same, regardless of the orientation along rotation. And there's no ether. He says there must be no ether. So now they're really freaked out because they know light travels. It behaves as a wave, but there's no ether to carry the wave. Now, it turns out around the same times, there's this guy named Maxwell. You've heard of Maxwell's equations? Mm-hmm. Right, same guy. It's not Maxwell from Maxwell's Donuts. This is Maxwell from Maxwell's equations. All right. He had recently determined. Now, he had done arguing from first principles of how electric fields work and how magnetic fields work. Okay? If you take a wire and you take a magnet and you move the magnet across the wire, you can make an electric field. The moving magnet, not the magnetic field, but the moving magnetic field creates an electric field.
Yes.
All right. And the moving electric field creates a magnetic field.
Yep.
Okay.
That's you throw a magnet through a spun copper wire.
Yep. And you get that thing. Or you run a current through the copper wire and you can
introduce a magnetic field.
Right. So you can do those things. Right. And they tend to propagate then across each other. And he figured out from first principles that these electromagnetic waves, this propagation of these waves against each other, should travel, according to computation, at 186,300 miles per second. And they were like, wait, I've seen that number before. That's the Michelson number, right? That's what Michelson figured out.
That's the speed of light. Yeah.
That's the speed of light. So they figured out that electromagnetic waves traveled the same speed as light waves. And the only thing that made any sense is that light is a propagating electromagnetic wave. But there's no ether to carry the wave. So
how does it propagate?
Well, so how does it propagate? And what are we measuring its speed relative to, right? So I measure the speed of sound relative to the air that it's sitting in or to the water that it's going through. But what am I measuring the speed of light relative to if there's nothing that it's going through?
Well, on Earth, it was going through air with Michelson.
It was going through here, right? But in the solar system out there, in the vacuum of space where there used to be ether, but they took the ether out, and now there's nothing there.
God was like, no more ether for you.
Yeah, cosmic vacuum cleaner took out all the ether. So when we're measuring the speed of light, what are we measuring it relative to? Okay, and they were like, this doesn't make any sense. How do we do this thing? Who's going to answer the question? Guess who's coming into the picture?
Charles Schultz.
No, it's Snoopy and Charlie Brown are not involved.
Oh, okay.
Einstein figures it out, right? And Einstein will tell us how to measure it relative to. He will figure that out the next time we get together to talk about light, and that'll be episode 4, I think.
Episode 4. Is light relative to itself or to a standing object? And I'm sure we're going to get back to Newton, right? And Galileo and relative bodies to each other, inertial reference frames.
Yeah,
right?
We're coming back. It's all going to come back. Remember, we spent a lot of time on the inertial reference frames and what relativity really means, and we're going to talk about Einstein's understanding of what relativity means and what these new findings by Maxwell of Maxwell's Donuts. We're going to figure out how all these things fit together is what we're going to find out. So
yes.
That is what we will find out next time when we talk about light.
Well, good. And in the meantime, we invite everybody to seek the good, live virtuously, and flourish, and enjoy the adventure of life. it's going to be a great day.